C'est quand c'est maintenant. C'est bon, on est en ligne.
T'as mis le parlant?
5 minutes. C'est bon. Tu vas pas comme ça. Ah. Faire ça. Juste la laisser.
Okay, welcome everybody to this second opus of the GERAD Julia workshop. It's great to see that so many of you came back after the first workshop. Julia is really a language that, in my opinion, has taken off in a very small amount of time in the scientific community, but also elsewhere. But really, in particular, in the OR and optimization communities, it is becoming a very popular language. And so today, in the second workshop, we were lucky to have we have a visitor from Brazil, Abel Siqueira, who will give the first part of this workshop. And the second part of the workshop will be given by Mathieu Panot and Alexis Montoison, who will talk about JuMP. So this first part is going to be about some optimization infrastructure that is developed right here at GERAD, and that we call JuliaSmoothOptimizers. So I'll let Abel give his presentation. Thank you.
Well, thanks, Dominique. Thanks, everybody, for coming. I hope you're all as excited as I am to see Julia and optimization to take off very fast, especially if you're using our packages. Who knows Julia already? Okay, great. Who doesn't know Julia, but like know Python or MATLAB? So I think that covers almost everyone. That's great. So for those who know Julia, you'll be very acquainted with almost everything. We try to make our packages very readable. For those who don't only know MATLAB or Python or something like that, you're going to see that's very similar to those languages. There's not a big gap on what you need to know, essentially just syntax. So my name is Abel Siqueira. And you can find this talk here in Talks, which is aptly named, Modeling Optimization Tools in Julia. But don't try to install it right now because it's not going to go well. It's going to take like half an hour. It has to download like 15 packages. But you can just use it to see the HTML if you want, which is the compiled version of, where is it? Of this notebook. Okay, so I'm gonna leave that. I'm gonna leave this link here. Well, I think it's easier if you just search for Abel Siqueira in Google. Okay, so these two first comments here, just in case nobody knows what Jupyter Notebook is. So this type of presentation is used for when you want to write some things, present some images, which are like in a static file query form, but also you want to show some coding. So this is very much used in coding classes, which have a lot of text. So essentially, if you don't know what the notebook is I'm going to run the codes, and you're going to see the result in real time. And these first two commands are installing everything, okay? I'm not going to run them again because they take a lot of time. But when you download this notebook at home, you can just skip and change to false here and run this. So it's going to install everything at the version that I used, okay? Well, unless I update this one, but probably not breaking versions. And I'm not going to run, so just look at this status, and you can check what I used. So now to the actual JuliaSmoothOptimizers. So me and Dominique, about 4 years ago, started working on a few Julia packages for continuous optimization. Essentially, we started porting a very famous collection of problems, which is the cutest collection. When we started porting, he already worked with Julia for like, I think, another 2 years. And when I started working on that, I saw that it was very, very easy to work. And I always used MATLAB before. or C++. And it was very easy to use, very fast, and it was essentially nice. So when you are more of a mathematician than a computer scientist, you want something that feels nice to use because you don't know a lot of coding. So that hit the right spots for me. And so I've been developing optimization packages in Julia for a while now. And JuliaSmoothOptimizers is an organization that we created that branches that, umbrellas everything. I'm not sure that's the term. But it's an umbrella for all our packages regarding the subject of Julia for continuous nonlinear optimization. In particular, some of these things can be used in the well-known machine learning area, but I talk a little bit about what we can do with our packages that are related to machine learning, but we look at the more generous continuous nonlinear optimization. So this is me and Dominique, and this is our amazing logo. Okay, not going to talk about it a lot because it's clearly amazing. So these are level sets of a specifically designed function to look like the Julia symbol. So it took just like 20 hours to do it. Just using my time. So what is the JuliaSmoothOptimizer organization and packages? We have a collection of linear algebra and optimization tools, and we made them for researchers, essentially us first, and people who wanted to develop code. That means not the end user so much when we started developing these things. So people who use fmin_unc or fmin_bound or fmin_con in MATLAB, they want something that just works. We are trying to make packages for people who are developing fmin_unc, fmin_bound, fmin_con. So the people that are working with optimization, that are trying to publish papers in the area. And of course, that grew a lot. So a lot of what we do can be just used. It integrates well with MathProf-based JuMP, which you're going to hear about later today, which is a big deal because you're going to see that JuMP is easy to use. So you want to integrate with that. And we have started to develop a few solvers for possibly competing with other well-known Julia packages. So essentially, we are working on a solver right now that I'm going to talk at the end. And we have a few solvers implemented already in our packages that are focused for large-scale, sometimes factorization-free methods. Okay, essentially cutting-edge solvers as we can. Similar work has been done in Python optimizers. If you know Sylvain, for instance, you may have seen some things like what I'm showing you today. So our packages, these are like 90% of our packages. They are essentially clustered into 4 parts. You have the linear operators, JL, which is essentially linear operators. It's used extensively in Krylov and NLP models, but it's the base of our packages. But the main package I want to talk about is NLP models JL, which is where I think we have developed most and what we have that's so much different from what other people are doing. So NLP models JL, it provides an API for you to access the functions of a problem, like the objective function, the gradient, the constraints, and everything else. And by providing an API, a generic API, you can work on your solver and rely on that API. You just change what the problem came from, the provenance of what you're using, but you have the same solver. So that's the main thing for today. That's it. Remember that, especially if you already know qtest from the area. If you've seen someone publishing a general optimization solver, you'll see they will compare with qtest. Okay, so qtest is like our main collection of problems. It's the largest collection of problems, I think, for the nonlinear continuous differentiable optimization. What else? So NLP models has an API for everything. And we also have other NLP models that we can create and access using the same API, particularly NLP models JuMP, which, as I said, integrates with the JuMP modeling language. And we have a few other packages, which I'm not going to go into details. On the other side, we have Krylov and a lot of other linear algebra packages. Essentially, we want to solve linear systems a lot. I hope everyone had like a basics optimization class, or is having, I know you. And you will know that a very large part of solving optimization problem is solving linear systems. Essentially, you want to solve linear systems efficiently, and you want to do it by using the most information you have, and you want to do it in different ways to get different properties. Essentially, what I'm doing is, what I'm saying is, you can factorize or you can use iterative solvers. When you want to factorize or use iterative solvers, you want to know what kind of problem you're solving. Is it symmetric? Is it positive definite? Is it a least squares, least norm problems? So we have a lot of packages around that are wrappers for well-known libraries for optimization. For instance, HSL and months are well-known. And we have a few other packages. There are many packages that I've been through here. A few other packages that are implementations or translations of well-known packages. We have especially Krylov, which is a package containing a lot of iterative methods of the Krylov type. If you know Alexei, he's working with that a lot now. And Krylov is how do you say it? Distance itself from other similar packages because it has publication grade methods. So I'm going to show you the list in the end of this talk. There are 4 papers related to Krylov with publications, like things that did not exist before and where they were created and put in Krylov. And there is also a book that cites Krylov. So it's really high grade, although it doesn't have a release yet because we have a backlog of functions to review. But except for that, is very high grade and very efficient. And the last part, we have OptimizeJL, which uses benchmark profiles, which is what we are working a lot now to get to the selling point of our JuliaSmooth package, like the whole thing, the JSO. I'm just going to say that, JSO, which is you're going to produce your solver, and the small parts that are similar to what's already done, you don't want to redo. For instance, you want to have a line search, so you can just go in Optimize and take a line search and put in your solver. You want to use trust region, you just take and put it there. You want to, for instance, you want to have a sub problem that is a little bit more difficult, and you can call an inner solver, for instance, what we have for unconstrained optimization, and you use that in your solver, and you can see if that works, and maybe you can just make something more specific later. So it's supposed to have a lot of things in there. When you do that, that's just one part, you're going to have to compare your solver to other solvers. So we have benchmarking tools in there. So you have the IPOpt solver. You want to compare the IPOpt solver with your solver. You can do that with one command in Optimize. Okay. I'm not going to. I don't think I'm going to show you with Optimize here, but I'm going to show what I mean by saying you can just call benchmark solvers and get a table, and you can just call benchmark profiles later and get a performance profile. So essentially working on cutting the preparation time for publishing new solvers. Okay, so let's get into coding. Just a disclaimer, what it doesn't have, we don't have integer programming, essentially anything integer at all. It may be extendable to integer variables, but we haven't touched that, and we're not gonna touch that, at least not in JuliaSmoothOptimizers. But one try, that's okay. For linear programming, we don't have something specific, but we can have an integer point method some ease. We just separate the time. Yeah. It doesn't have its own modeling language. So essentially, if you want to create a problem, you rely on a few other functions, or you give it everything by hand. So you can create one problem with JuMP. You can create a problem by using automatic differentiation. You can create a problem from Qt, Ample. So you can create things using other packages. But we are not going to implement our own modeling language, essentially because it doesn't give anything new for us. And it's not a complete replacement to Optim. If you know Optim, Optim provides a few solvers for the user, something like the fmin-unc. We do not have our own solvers yet, but we'll look into that. Okay. So NLP models. Essentially, what's saying here is what I told you. We define nonlinear programming models and an unified API to access them. Models are different. We don't assume many things from them. For instance, some models provide sparse derivatives, some do not. Some provide matrix-free products. Essentially, you don't create the matrix, you just get the information of matrix times vector. And if you want to create something that's a little bit different, if you want to extend the method, it should be easy. So we're gonna put some examples of how to create a new model type. So what I have here, using NLP models, which is our package. This first package uses forward diff, which is a forward differentiation tool. And you just create an AD-NLP model by passing the function here. This function is the Rosenbrock function, should be well known. And a starting point here. So first things first, this is the most basic thing you can do. You just create a model with a function and a starting point. AD-NLP. Okay, now something a little bit more interesting. Qt. Qt is a famous library. Okay, that's understand. RosenBR is the same problem. So this problem here, which, as I said, it's a very famous problem. It's already implemented, of course, like maybe 30 years ago. Qt model, RosenBR opens that problem. Okay, it's in Fortran, it's efficient, it has all the information you could possibly ask for this kind of problem, and you just open it with Qt model RosenBR. Okay, I like to say that every time I talk about this for a younger audience, it's like nobody, fine, that's okay. I don't see the point of that. Okay. Well, for a little older audience, what does this mean? It means that you don't have to spend like 1 hour compiling Qt model because it's already doing that. And you have access to the Qt in a high-level language that is not MATLAB. And it's better than MATLAB in that sense. I'm underselling a little bit MATLAB. Okay, I don't have. So this is like one command, you have a Qt model at your hand. And last but not least, you have the JuMP model. So I'm not going to explain the full JuMP, but M equals model creates a model in JuMP. It's not NLP models, okay? At variable says which variables does this model have. So this M goes here, x1, 2, means it has variables x1 and x2. And set value says which starting vector it should use. So essentially the same I'm doing there. And at NL objective mean in the same function. Okay? These 4 lines are JuMP. I don't have anything to do with that. They are another package JuMP. What do I did, or we did here? NLP model JuMP. So this model is created. I pass it to mathprog NLP model. Now it creates an NLP model which has the same API as AD-NLP and CNLP. So what is this same API I keep talking about? So here I'm going to do a simple for name NLP. So name NLP in ADNLP, CNLP, and MPNLP, which are the three NLP models I created. This for essentially is gonna pass through these three values. Autodiff, QTIS, and JuMP here are just the name, and NLP are the variables contained in the problem. So for each iteration of this loop, NLP is a different NLP. I hope that makes sense.
Yeah.
So I take x equals NLP.meta or meta. NLP.meta.x0, which is the starting point. Print model name. This dollar sign. This dollar sign name is gonna get the name and put in there. fx equals obj NLPx, gx equals grad NLPx, and big H x equals hex NLPx. So what's the API of JGRAD and has? Of JGRAD and has, they're gonna get the objective function, the gradient, and the hashing of NLP, whichever NLP it is. Okay, so three different NLPs from three different sources. You just run this, and it shows the information of each NLP. So the first one, I can just go here. So the first one, autodiff, the function value at the starting point is 24.2. The second one, the QTIS, also have the same starting point and the same function value, and JuMP as well. Okay, notice that QTIS does not give, I did not pass to QTIS a starting point. It's already in the file. It's already predetermined by the program. So fx, gx, and ajax, all this information I took the same way, okay, from all three different models. Notice that I only pass the lower triangle of the matrix, because I'm not going to pass everything that's repeated. It's a matrix. And notice these two other models are sparse, and the first one is not. Okay? So why is this cool? Because it allows me to implement a modified Newton method, which is to find a row K positive, such that this matrix is positive definite. This is the hashing plus something. Then I find the solution of this system, and then I find an alpha K positive through backtracking, such that that inequality holds, which is the Armijo inequality. So this is like basic unconstrained optimization. Maybe not so basic, but this is in the basic classes of mathematical programming. So how do I implement this? Using linear algebra, function Newton, my first argument, and the only argument that matters here, which is the only argument that is not optional, NLP, abstract NLP model. Okay? So this is what we meant by saying you should implement things following the same structure. Or I think I say that. Follow the same structure, which is receive an NLP model. Okay? If you receive an NLP model, abstract NLP model, it's going to work for anything that I pass. So I also changed the starting point, the tolerance and relative tolerance. I have some stopping criteria for if it's doing too much work, too many evaluations, or it's taking too much time, essentially because I don't want to break. I have a t equals L type x here, which I'm going to ask you to ignore for now. And I compute a few values, essentially the function here at obj, the gradient here in grad exclamation mark, which is an in-place version of the gradient, and which does not create any more memory. I verify that I'm not at the solution, solved and tired. And while not solved or tired, I'm gonna do this internally here. So the first line, Ajax computes the hashing. I'm declaring it a semantic matrix because I'm using a simple Scholastic function. from Julia. I use lambda equals 0, and I test to see if the Scholastic factorization is successful. If it's not successful, I increase the lambda, compute Scholastic again, and repeat. Eventually, I'm going to find a lambda such that the matrix H plus lambda I is the positive definite. Found that, compute the step, slope starting at 1 t is 1.0. Armijo backtracking. Okay, I'm going to go into that. This computes x squared plus 1. I update my x, my f of x, my gradient, norm of the gradient, and I see if I stop or not using solve entire again. So this should work. If it doesn't work, it's going to say it's tired. And at the end, we're going to return x, f of x, norm of gx, the time, delta t, which was the elapsed time, and eval obj NLP, which is the number of evaluations of the objective function. Same thing for the gradient, same thing for the hashing, okay? Run this. I'm gonna open the problem of Rosenbrock again because it was finalized. There is some library things happening. And this is me running Newton method, where? Here. Running Newton method on each NLP, DNLP, CNLP, and PNLP. The results are essentially the same. Okay, the first one is the automatic differentiation. I'm going to run again so we see that's not like the pre-compiling happened. All time is on the same order. The number of function evaluations, gradient, and hashing is the same because they are the same models. We're not doing anything different. But the main part is I use 3 different sources of problems, and I use the same model, same solver Newton that I implemented. Okay. So ADNLP is quick and dirty. It uses 4diff, which has dense matrix, is not has, but it's easy to write small problems. You just want to write Rosenbrock and see if it works. You're going to teach a class. You're going to write something quick and show the student. You do it. You prepare your slides and someone say, but what if you put x to the power of 4? And you're okay. I want to change them. That's it. It's working now. Okay? So it's very easy to use. JuMP MPB. Well, JuMP is a complete modeling language. It's great. It has a lot of things, but it's a complete modeling language. You have to install that, and you have to make sure your students have the same version, current problem at least. And you have to make sure it's, how do you say, you have a, well, you know sufficiently about the JuMP to use it. And QTIS is a traditional package for benchmarking in publications, okay? So what's the framework? You get an idea, okay? So the idea may be, I just need to implement a solver to get a passing grade. The idea may be, I have an idea for a new solver, or the idea may be just, well, I don't have anything to do on this, like on this summer, and I'm going to implement some textbook things and make a pull request to JuliaSmoothOptimizers. Like crazy idea that I had. Have the idea, prototype. You prototype, test with ADNLP. So you just write a quick function. That one took a little bit more time, but you can write something very quick. Just use the, how do you say, the backslash? Use backslash for solving system. Okay, and just hope it works. Prototype, test with simple models that you implement by hand. Is that working enough for you? Yes. So you can now use QTIS, for instance, and test it, compare. Maybe your basic idea is enough for your numerical results and for you to submit a publication. Maybe not. And possibly you can show an application. So QTIS, you show it like 1,000 and something problems. I'm not sure how many. You just compare your solver and another, see if they work better, which one works better. And maybe you can show an application, implement the application with JuMP, so you don't have to suffer a lot, and run all with the same code. Okay. So there is a small, a kind of two-language problem in optimization. What usually happened in this stage when I was young? Prototype with MATLAB. Okay. Test with whichever MATLAB you're using, whatever. Possibly something like ADNLP, but usually people would have the function that gives everything. Test with qtest. Well, then you start to suffer a lot. Maybe it's working, maybe not. If it's working sufficiently, you just finish it and say, okay, this is the publication. These are preliminary results we have made. Shows that we have great progress to do, but we need to go to a more efficient language to really compare with the live solvers. So what will happen at this point? To improve, you will have to change from MATLAB to Fortran or C or something else. You change your prototype from one language to another. Now you have you have to stop whatever you're doing to implement essentially everything again, in hopes of showing that your solver is indeed faster than the well-known other solvers. Okay, so this hopefully solves the two-language problem. If I phrase like that, you don't need to explain that there's another two-language problem. You can pretend that this is the main language problem. Essentially, the main part of my presentation is selling you guys these things. Okay, implementing things with NLP models should be the new way to do it. Of course, it's my package, but I have to sell it. But it's really easy to use, and you can see. But now to talk about the other things. We have other models in here. Essentially, AMPL is another modeling language, which we also have. There are QPS and NPS files, which we also can read. QPS is for quadratic problems. I put some for/slack variables in there, which should be removed. It's missing something else. Creating a new model is not hard. I was playing around the other day. I was trying to create something. I intended to start, but it's probably going to take more time than I want. A simple model to you take data like the X and Y, and you say, okay, this data I'm going to create a maximum likelihood model for this data. So I was thinking about doing something like that, but it's probably going to take a little bit more time than I have at the disposal. But it's a good idea, for instance, something to do. So there is more to the API. I just showed you like 3 functions. We have like 15, maybe 25 for accessing every function in all its derivatives up to the second order, including constraint problems, of course. This is the general format, minimizing a function f subject to a c of x between 2 bounds and the variable x between 2 bounds. So if you want constraints, for instance, you can just say that CL equals CU. And the NLP.meta stores a lot of this information that are not immediately available. So here I create another problem which has a lower bound, an upper bound. It has a constraint function. Then it has a lower bounds for the constraints and upper bounds for the constraints. Here I'm just selecting the meta. I have here the starting points, the lower and upper bounds for the variable, the lower and upper bounds for the constraints. Which kind of variables are these? Are they fixed variables, free variables, lower bounded variables, upper bounded variables, both lower and upper bounded variables, and essentially the same thing for constraints? Are these equality constraints, free constraints, which hopefully should not appear here, lower bounded constraints, upper bounded constraints, or both bounds there? So hopefully everything you should ask from a problem, it's in there, which can be inferred. IPOct, as I told you, is a well-known solver. It's, I think, the main open source solver to compare in general optimization right now. So this is how you can use it if it was installed. Currently it's not installed. Let me add that up here. which I don't know if I should add IPOps at this time. Maybe we'll come back later for this. But if this is working, which was my computer, you can just run IPOpt. Here you have an NLP. You pass that NLP to IPOpt, and it's running now. This is working, and it has been tested for a while. This is what we've implemented like last week, I think, which is running IPOpt directly. Okay, so essentially you have an NLP. Here it was working apparently. I'm not sure what's happening. Well, that was supposed to happen. Ours is better. That's obvious. So here we have NLP models IPOpt, which is a new package using NLP models and IPOpt at the name. So IPOpt called directly into an NLP. So what we're planning to do with this, we're going to adjust it into the Optimize API, so you can run benchmarks over your solver and API in 2 lines. Okay. So extension of NLP models, nonlinear least squares. Nonlinear least squares is it's how do you say? It's getting a lot of attention because you associate nonlinear least squares with regression, nonlinear regression, for instance, and because of that, it's getting a lot more attention than a few years ago. Although that relationship existed for a few more time than that. The difference is that a nonlinear least squares problem has objective half of the norm of a big F of x squared, which is the sum of small functions fi squared. Okay. In particular, you can have the sum of linear functions. I'm just going to say that again. Okay. Which is the linear least squares model, which is the linear regression or sometimes polynomial regression that you already know, hopefully very well. The nonlinear least squares is an abstract nonlinear model, NLP model, so you can use whatever I was already using with that. But of course, when you're working with a problem like this, what you really want to do is use the information that you have a big F in there hidden. You want to use big F directly. You want to just compute this Jacobian and implement something that uses F and the Jacobian directly. Okay, so LLS model just creates a function F, which is AX minus B. AD and LS model is the automatic differentiation. Same thing I did for NLP, but for NLS. And MathProg NLS models uses traditional JuMP. There is an exclamation mark there because this is very important. Okay, you have to trust me. You just have to trust me. Essentially, what we did was use the same JuMP modeling language that you're used to, or will be in a couple hours, and create that big F from those models, while also retaining the possibility to have constraints, which is the new thing. Okay, so I'm just going to show you a quick example. I generated this data. It's nothing important. It's just random. I'm going to use here this quadratic model, which means that I have a matrix 1s, x, and x squared. And I'm going to create a linear least squares model, big X and Y. So when I create this model and I use Newton, which is the same solver to solve it, I'm actually just solving the normal equations for the linear least squares problem. Okay, I'm doing that very inefficiently, by the way, because it's a non-specialized solver, but it works, which is great for showing things. Here, h of x is creating the function with that. Scatter and plot just shows the result. Okay, so live here you have the solution of a linear least squares. Okay, like not a big deal, I know, but we like that. Linear least squares, try CGLS. So Krylov, as I said, is a collection of iterative methods If you use CGLS, you have the advantage of not creating the matrix. It's actually already created here, but not mine. But you can also just use the multiplication of the matrix by vectors. Okay, essentially matrix vector products. It's also an iterative method and is specialized for linear for least squares problems. So this is much more efficient than what I did up there. Okay, so if I just use here this data that I just computed, I get the same solution because it's the same problem solved the same way. Okay. As I was saying, Krylov has a lot of methods to solve the same problem. You can use CGLS, CRLS, LSLQ, LSMR, and LSQR. Few of those are were created. Two of those, I think, were created a couple of years ago at most. One of them was created and published by Dominique and others et al. I don't know who was so sorry. Linear least squares with regularization. So just to add regularization here to show that I can do it, I use lambda equals lambda here in lambda equals 1.0, and it solves the problem with regularization. It's not much different, but here you can see how it gets different using regularization. It's indirect, so it's a little slow. And you can just see almost no regularization. And for this side, a lot of regularization to the point it loses the data information. Okay. Essentially, I wanted to show an animation. No, it's just essentially you can do regularization in there, and it is working as a regularization should. But as I said, you can do nonlinear least squares. So this is a traditional nonlinear least squares problem. Is Turber. I took it from that side, and the data is this one. And the site also gives you which model it should have. So the model you should have is this one, which is a rational function, x cubed, cubic polynomial on top and a cubic polynomial on the bottom. It's very hard to solve this thing because it's awful and it can get close to zero and explode. But luckily, I'm using the starting point, which I'm not sure is the correct one, and solving it with Newton, which is a non-specialized solver. So again, this can be made better if you use a specialized solver. But just to show that you can model nonlinear least squares here. And the part which is the the residual function is just this. Age of beta x is my model with parameters beta at point x, age beta x minus y for each I equals 1 to n. Okay? So this is my residual function. Okay. Now I'm just so after you use JuMP, you can come back here and see how to create a nonlinear least squares with JuMP. So this is the same thing I had before, a different model now. Variables, nonlinear expressions, and then you create an expression here. And notice the nonlinear expression, I'm passing this f, big F, for each data. And I create the nonlinear least squares by passing the model and the expression. So what it does is it uses the model information. It could have constraints, for instance, and it takes that expressions that you passed it and uses those as residual. Okay? Solving again with Newton and showing the data same way again, you're gonna have these results. I used the other data because it was easier and faster. Okay? You can modify models, so you possibly know how to create a quick model, a quick solver for one problem, and you want to test in another problem, which is not the same format, and you can modify it. So the simplest one, the most useful possibly is the select model, which just takes the inequalities and converts to equalities and bounds in the variable. Okay, but you have a feasibility residual, which takes a problem where you want to find x such c of x equals 0 and converts it to a non-linearly squared problem. And the feasibility form NLS, which takes this problem, which is awful if you don't look at f specifically, and converts it to a problem where you have f explicitly, although it's in the constraints. It's not an unconstrained problem anymore. So it's harder, but you have a lot more information about f now. Okay, other modifications are planned, and we can do a lot of things with this. As I said, we have a lot of more models here. I just put the list of them. And these include 2 packages, optimization problems and NLS problems, which we started to gather a lot of problems already implemented in Julia. Essentially, pure Julia problems. So optimization problems has problems in JuMP format, which is good for either our packages or other packages. But NLS problems uses this new mathprog NLS model, so it's specifically for our model. We have a big problem now, if anyone wants to work on that and try to implement something. How do we classify and select problems in an efficient way? Something that's easy to create a new problem and add to the collection. So Qtest just has a big file with the information of the problem, so the basic information there. Well, not so big, but most of the information he can gather is there. Okay, and what do we do to select? We usually just go and look, oh, I need this thing here, and parses the whole file and selects those things. But when you want to create a new problem, you have to go in there and check everything. And sometimes things happen to be wrong, and you have to open a pull request to fix it. So it's slow. I tried to create something, but it's abandoned for now. So maybe someday. As I said, I have optimize, which is the end game, non-related to adventure, the end game for our JuliaSmoothOptimizer. So optimize contains tools for line search and trace region methods. It already contains something now. We want to put many more things in there. It contains tools for benchmarking solvers, which return data frames, which is awesome if you want to get a lot of information. And it has a few optimization methods as well. So I'm going to use for this section optimize, benchmarking profiles, and logging. The first thing I'm doing is collecting all Qtest problems with up to 2 variables of the unconstrained type. Then I'm creating a generator, which is a Julia thing, or maybe not just Julia, but it's a Julia thing that creates the Qtest model from that list of problems. This is necessary because Qtest can't be open, can't open more than one problem at once. So this is hack, possibly, but a native hack. So it's by design. And solvers is both solvers that I'm considering here. LBF.js. So the first one with a column is the name I'm giving it, which is the same name as the function, LBF.js, which is our solver, and trunk, which is the trunk method. So LBF.js, I'm not going to go into details, but LBF.js uses the linked BF.js factorization with line search, and trunk uses inexact Newton with first region, yeah. And it solves by the conjugate gradient with stayhog. With stayhog? With stayhog. Yeah, that's great. Stats equals benchmark solvers problems. Run. It takes maybe 10 seconds. Well, it was exactly 10 seconds as I planned. And sorry. So these stats here, they are a dictionary for each of these solvers, LBF.js and trunk, and it provides a data frame with all the information it gathered from the solver. This is limited by the solver, essentially. If the solver wants to give more information, it can give more information. But the basic information contains 29 columns. So here is the df equals stats trunk, which gets the data frame from trunk. And you're seeing it here. First column, the ID. Second column, the name, number of variables, number of constraints, number of equalities, status, or the exit flag of the solver, objective, and so on. All the information is here. So if you use data frames from R or Python or pandas in Python, something like that, you know that having this information in a little more high-level format is very useful. For instance, you can just get the 6 first from these columns, and it also provides the column. And you can create a LaTeX table from that information. In particular, this LaTeX table is from our Optimize. It's unmerged yet, so highly data level, but it's a LaTeX table that you just can take and put on the publication directly, and it's just new. I know. So of course it's a little cluttered at the moment. Maybe we can improve it, but I'm not sure yet how much we can improve. It's already amazing, so I'm going to stop here. As I told you, there is the performance profile. So the performance profile is a little bit difficult to explain in details. This command is getting the data frames elapsed time and this hack, which gets either 0 or infinity. If it's a first order status, that means it worked, it's 0. If not, that means the solver failed and it's infinity. So this is a matrix of costs. So how much time it took to converge? 0001 for the first problem for trunk, and 001 for the first problem for LBF-JS. Except here in inf, where it didn't converge. Did not converge. Okay. So essentially, this gets the matrix and performance profile P, and the names of the solvers. This is the performance profiles. So the performance profile is a very traditional tool to compare solvers. These are comparing which are more efficient solvers. This is a percentage of problem. Each point here is the percentage of problem, but specifically here is the percentage of problems solved faster or at the same speed as the other solver. So trunk, which is the blue one, has solved about 60% of the problems at the fastest speed, and LBF-JS about 40%. Okay, so this line is called, this side is called efficiency. So you have the 60% efficiency, 40% efficiency. Each step here is like, but what if I gave it a little bit more time? So what if I gave it, like, here is a log scale, is this log 2?
Log 2.
So what if I give it 2 to the 1 more time? If I gave it twice as much time as the best one. So if I gave it twice as much time as the best one, it would have solved this much problems, and the blue one would have solved this much problems. Very simplified analysis. When I go to the other side of the table, to the infinity, I get to the place where, what if I gave it as long as time as it needed? Would it have converged? So yeah, essentially, you say the amount of problems it has converged. So it's the robustness of the method. Efficiency, robustness. Okay? So that's like the elevator pitch for performance profile. Okay? Hope I can convince you. As I told you, we are not yet providing a full alternative to opt-in, but opt-ins, one of the opt-ins method is LBF-JS. It has another method for trunk, but this one is easier to access. This is my wrapper around opt-in, which calls optimize, and opt-in method using our NLP it passes the information Optimus need, essentially because I'm going to use our benchmark interfaces to work to compare solvers against Optimus. Just going to run this too. Three actually. So first, this is the elapsed time. We are still looking at problems with at most 2 variables. We start with much lower efficiency than Optimus in time, which is a good point for them. And eventually we solve, I think, 98% of the problems. I'm not sure, 95 to 98% of the problems. And Optimus, it's a little bit down there. So why are we so much slower if I'm selling it so much better? Essentially because we haven't ironed out the type stabilities issues we have. So this is one of the hardest things in Julia. So figuring out where you have some stabilities, some type stabilities thing. But essentially, it's irrelevant in higher dimension, in higher problems. But I'm not going to run them because it takes like 30 minutes. And I'm not going to wait for that. On the other hand, I can say that we are a lot more efficient because this is looking at the number of function evaluations. So this is considering how many function and gradient evaluations our solver and Optimus solver are doing. And we are always better. So that means that I have solved 98% of the solvers faster than Optimus. But what if I gave it twice, or in this case, 4 times as much evaluations than I took? Well, he would solve a lot more, but I'm still solving most of them. And that goes on for all the way until the end, which I have more robustness. So essentially have a much faster solver if we can solve the type stability issues. Why haven't we solved that yet? As I said, there's a backlog of things to do. Alexei made like 700 pull requests. You have to parse all that. About minus 600. And so this is essentially trying to say we still have a good solver even though we have failed on these small problems. I actually have run the solvers in another time, and we are indeed faster if I consider problems which are much larger. So, but they lose a lot in the smaller problems. A little thing in the smaller problems make a lot of difference. So just to wrap up, what are we doing now and what are we planning to do later? Multi-precision support across many packages. So one of the things that people are trying to do now, for instance, with GPU cards, are taking, for instance, the neural network, running it with a half precision, just getting to a good point, and then changing to quadruple. These are all hard words for me. Quadruple precision, and then you can get to a good point, good precision. A good tolerance for what you're looking for. So essentially, you want to work with different precisions, and this is NLP model with AD NLP model, which is the automatic differentiation one. And this line here, I'm running it. It's the original one, the first one I made. I'm running it just like I did there for Rosenbrock function, and I found a solution. Okay, nothing new here. Essentially, the first thing I showed. The second one, I'm running the same problem in 32 bits. So you have not noticed, but I made 3 changes in the code originally. The thing I said, don't pay attention to this. And then a point where I should have written 1.0, and I wrote 1 of t. Essentially, those things make possible that I can run code 32 in our code. So essentially, AD NLP model is already multi-precision ready. 32 bits here is native to Julia, is hardware native, not very fun. 16 bits, it solves here. You can see the solution is float 16 this. The solution here is written in any way. And here in, I think, 256 bits, which is a native bit float. I mean, native actually is the MPFR from GNU. These are all like, I haven't installed anything else from what I installed earlier to run. Everything's running in multiple precision here, okay? So we are already multiple precision ready, but it would be very nice to work with GPUs. We haven't started working with GPUs yet to see how much faster we can make things and how much fun. We are also looking at the general solver, so I'm working with that right now. Actually, here I don't show the solver, I just promised. So I have trunk, as I said. This is trunk running on that same problem, LBF.js running. I also have a bound constraint method. It's the same problem, except that x2 is bounded by 5 from above. So the solution is different. So now I have bounds on the variables. So we have two good solvers for unconstrained, one good solver for bound constraint. And I am working right now, Dominique, on a solver for nonlinearly constrained least squares. With nonlinear least squares. Well, we plan to extend it in a few more months to more general problems. So essentially, we're going to get to the point where we can compare against the full opting package. Just this try. Let me just see how it goes. Just see if we do much better. We are looking into large-scale problems. Okay, we want to solve things which are very large. We are also looking at an NLP models extension, which is a sum of functions plus a sum of nonlinear least squares term and a linear least squares term. It's a huge code refactoring that I'm doing, but it's also an extension that allows separable functions. In particular, you can ignore the other things and look at just these things, and you have all functions separately, and you can implement, for instance, stochastic gradient or work with the objective problems. I actually have tried stochastic gradient, but with my implementation, which is not good, it works. So I can already say that this is super cool, which is a technical term. Parameter optimization, or for the machine learning people, hyperparameter optimization. We're gonna try to do it automatically. So you create a solver, or for instance, think about trunk, which you already have. You say trunk here, tune trunk on these problems, you get optimal parameters. And now you say solver with parameters and the optim parameter, and you have an optimal solver for those problems. Essentially, in 2 lines, you can train your solver for those problems to get the optimal parameters, hyperparameters. That's your thing. So what we are needing the most now, so what we'd like, what we hope you can help us, give us feedback. So essentially, we have a few users, few interested parties, but we need more people, more feedback, opening issues. If you want to get involved, we have possibilities. And we also want to work on type stability, which is a major issue. It's the thing that's going to change most of our code because it has a cascading effect. So we also want to have more solvers. Of course, we want more publications. And our objective, possibly to the end of the year, is reach JSO 1.0. So these publications, 4 of those are publications, I think Dominique is in all of them. 4 of those publications are related to Krylov, and there is a book, 4 articles and 1 book, all publications actually. Some are related to Krylov, implementing new methods, and some are using Krylov. We are also working on 2 more papers using JSO, which is the one I told you about, and a paper for the complete JuliaSmoothOptimizer organization and practice. So that's it. I hope you have enjoyed it, and I thank you for being here. So questions, is that it? No? No, one at a time. So I think that's it.
You can already tune parameters of solvers, right? You wrote a DFO solver some time ago.
Yeah, this is semi-implemented, but it's only for the new NLP models version. So NLP models with the new changes, I have this implemented with a kind of nomad solver. Same kind. It's in there.
That's great.
Yeah.
And if no one has more questions, I propose that we take a 5-minute break, and then we'll come back from the JuMP tutorial. In any case, I think Abel is staying here for an extra week or two. Right?
2 weeks, I think. Yeah.
2 weeks.
So he's going to be around. If you want to talk about Julia, about optimizers or nonlinear optimization or something else.
Yeah, you feel free to come bother me and give me feedback. Okay.
Thanks.
Thank you.
Thank you.
Okay, so let's come back at 3:15.
Okay. So before we start JuMP, we're going to be two people presenting, myself and Alexis. I will be presenting the first part, and then Alexis will take over. So in the meantime, if you have any questions relating to installations, packages that have errors, a code that is not working, you ask Alexis at the beginning, and afterwards you can ask me while Alexis is presenting. Okay? So just to remind you, all the code that you need for this tutorial is on this repository. The URL is here. I'm going to try to zoom in a bit. No, I'll change anything. So you go to GitHub, then you look for me, it's Mtano, and then you look for tutorial JuMP. And you can clone this by copying this URL. And this will give you all the code, so all the notebooks, all the source files available on your machine. Okay? When you run the notebooks, right, the first cell is essentially reading a file that is called setup.jl and running everything that's in it. This will load all the packages that you have to load. You should not have anything to do manually. It should all be automatic. In case you have an error, you turn around, you look at the guy in the back, and he will help you with that. Just to say that we made a few modifications just before the workshop. So I invite you to update everything by doing a git pull from your terminal. So either you reclone everything from fresh to have the latest files, or you just update the repository by pulling from everything. Okay. So I invite you to open the first notebook that is called facility location and run this. It might take a little time because it has to download a few things and compile some stuff. And I will start by giving you a short overview of what JuMP is and how it relates to optimization packages. Okay, so this is where I want to do this. All right, so who has ever used a solver here? Anything like Cplex, GuroB, CVC, skip, non-necessary integer or nonlinear, whatever. So when you do that, in your computer, you're going to have some object in the memory that is a Cplex object if you're using Cplex, a GuroB object if you're using GuroB, IPOpt, and so on and so forth. So this thing is in memory. So it's the internal representation of the optimization model that you're trying to solve. Okay, that's very, very low level. You never interact with that directly. You interact with it through an API. So a set of functions that allow you to pass information and query information to and from the model. So if you're using Cplex, you use the Cplex API. Either the C API if you're doing C, or the C++, or the Python, the Java, the Julia, and so on and so forth. Okay? And whatever code you write for that is specific to that API. The C API for Cplex will not work with GuroB, and so on and so forth. So if you want to change solvers, then you have to redo everything for GuroB, or for CBC, or GLPK, or whatever solver you want to use. So it happens quite often that you start writing down your project. You're using Cplex, so you're using the Cplex API, and all your code is completely tied to Cplex. If you wanted to rewrite, to change your code and have GuroB, you would probably have to change a lot of functions that are specific to Cplex and rewrite them for GuroB. And that can be a big hassle. So this is why the people from JuMP have created something that is called Mapout interface. So this is essentially a generic API that covers all possible solvers. So any calls that you make to Mapout interface will be passed either to Cplex, to GuroB, or the solver. But your code is always only interacting with this orange guy. Meaning that if you want to change from Cplex to GuroB, you don't have anything to change in the orange part. This is still slightly low level.
the kind of functions that you would have here would be like add variables, get dual variables, do stuff, and over. So it's not the most user convenient thing. It's essentially some sort of a Cplex API that doesn't have Cplex in the name. FYI, actually what MapOpt interface does is it can also store a cache of the optimization model, modify this cache, and then pass everything in batch to the solver. That's fairly involved, so we're not going to discuss that today. Just remember that we only need to interact with one orange guy and then use whatever solver that we want to use. So far, so good. I see eyes rolling, or Dominique is like, oh my God, what is this? And finally, what we're going to talk today about is JuMP. So you have these things, those objects that are super involved, APIs that are very hard to use or very specific, a more generic API that is still low level, and then there's a nice thing, green, on top that is called JuMP, that is very convenient, very user-friendly, that allows you to model things, to create a model, to declare this is my optimization model. These are my variables, my constraints, my objective, and this is what I want to do with it. And today, we're only going to focus on this. So I told you about that so that you know behind the scenes what is happening. But today, I will not talk about MapOpt interface. I will not tell you how to do callbacks in Cplex. I will only tell you how to create models with JuMP, how to solve them. There's only one function to know, and how to query information from them. Okay, so it's a very high-level talk, very user-friendly, very convenient. If you have specific questions on how to integrate with a particular solver, you can ask them, but I would probably deflect and try to shift the focus to something else. Just to keep things simple. All right. So let's get started. So by now, this thing has installed a bunch of packages that we need. And I'm going to start by formulating with you some mixed integer, actually only integer problems that are based on the facility location problem. The point is not to solve the facility location problem. The point is to show you how to use the JuMP commands. So you probably have no interest in the facility location problem. It's fine. I don't have a lot of interest personally in my research, but I'm just going to use it to showcase a number of things. And the reason why I use that is because it's fairly easy to understand. So anybody already familiar with the facility location problem? Okay, a few people. So I'm just going to remind you a bit what it is. So we have a set of clients, end clients, and a set of facilities. You can think each client is like a bakery. Each facility is a warehouse where you have flour, and you want to know how many warehouses you need to build to properly serve all the bakeries, say in Montreal. In Montreal, probably you only need one warehouse, but if you're in a French city, then you would need a lot of them. And you want to do that, of course, at minimal cost. So here I started just going to take 2 facilities and 5 clients. It's a very small scale example, so I can show you things and print stuff on the screen directly. In practice, those numbers will be slightly larger, and so the problem gets more untractable. So we want to do things that are the cheapest, and we have 2 types of costs in the classical, easiest facility location. Every time you want to buy to build a warehouse, you have to pay something like, say, $1 million. So it's a high cost that is fixed. And once you build a warehouse, you can use it as much as you want. That's the first type of cost, fixed cost for opening the facilities. The second one is the cost for serving every customer. So think if I have a warehouse, then I need to ship some product from that warehouse to the client, that is going to cost me something. Typically, for real-world instances, these are related to distances that you travel, or more involved something, or a more involved quantity. But just to think of it, think of those fixed costs as how much it costs to build a warehouse, and then the CIJs are like the distance from a warehouse to a client. And in this third cell, I'm just drawing random values for the numerical examples to make some sense. So when I run this, I now have two variables in the scope that are called n and m, two integers, n is equal to 2, n is equal to 5. And then I draw the costs. So here there is nothing that is printed because I put this semicolon at the end. But if you want to check, so f is a vector of fixed cost. So if I want to open the first facility, it will cost me 8,744, and the second one is cheaper. It's only 1,082. And then you can do the same for the cost of serving demands. So Cij is the cost for serving customer I from facility J. So if I want to serve customer 1 from facility 1, I will have to pay 921. There is no question of how much product I ship from a warehouse to a customer. We assume that we just sort of like activate the links, okay? And then shipping the product is free. But of course, you could have things with capacity, as we will see at the very end of that example. So far, so good. So does everyone, can everyone run this notebook at the same time as me on your machine? Yes? Do some people have troubles going this far, or? Okay, great. So if we want to write what I just described with words as an integer program, this is the formulation that we would get. So we're trying to minimize the cost, that is the fixed cost. Every time I open a facility, this is a binary variable y multiplied by the fixed cost times the cost of serving all customers. So of course, I'm going to have a variable x that tells me whether I serve customer I from facility J. And the constraints are the following. Every customer must be served exactly once. So you cannot send 2 trucks to the same customer. And if you think about it, that would be anyway inefficient. But if you have weird costs, like this guy may be negative, and you may want to have like 2 trucks doing the same thing. If some very generous person is paying you to send trucks. And the second one is here to say that if you serve some customers from a given facility, then you have to open that facility. Okay, so if yj is equal to 0, then you can see that this sum here must be equal to 0. And so all the variables xij must be 0 for the given facility. And once I open the facility, yj becomes equal to 1, and then I can set all those variables to 1. Not necessarily all of them, but that describes the feasible space. It's a very classical, simple formulation of the facility location problem. And if you've taken the integer programming course of Guy Desaulniers, you probably have seen that example. So I took it from his note class. So now, you don't need to wait for me to fill in the gaps in the notebooks. And I invite you not to wait for me and try to fill in the gaps yourself. At the beginning, you will need me to show you the syntax for creating variables and constraints. But you can go directly look at the documentation or other examples and try to move faster than me. So the first thing is to create a model that we call model. Doesn't have to be called model, but it's a simple name. And then we're going to create variables. So I wrote the x variables and the y variables. So we're going to create x variables and y variables. So the syntax, you actually have several syntaxes. Here, I'm going to use the simplest one. I use a macro that is called add variable that is given by JuMP. I could do this, that it says I'm calling the add variable macro from JuMP. Okay, but here, because I imported JuMP, I don't need to specify this, and I can just remove it, and Julia will know what to do. So I'm creating a variable. I'm adding it to model. So then the first argument is always the JuMP model to which you're adding the variable. And I'm going to name it y. And y is a vector
that has n coordinates. All right? And this variable should be binary. So here, I'm creating n variables that are going to be y1, y2, y3, yn, and they're all binaries, and they're added to the model, like this. And if you give it a few seconds, here we go. So what is this? This is a vector of variable refs. So just some things that think of them as variables, y1 and y2. And now if I look at the model, it's a feasibility model because I didn't give it any objective. And the only constraints that it has is that y1 should be binary and y2 should be binary. Okay, and we're going to add an objective and we're going to add some constraints before we can solve it. So this was for y. So we can do the same for x. And x has two indices, I and j. So I just give it two indices. And it's also a binary variable. And so this will create you a two-dimensional, so it will represent it as two-dimensional. But of course, you have n times n variables in the model. And if you look again at the model, now you have all those variables that we just created. So serving customer 1 from facility 1, customer 1 from facility 2, customer 2 from facility 1, customer 2 from facility 2, and so on and so forth until the last customer. Okay? Now, you should know that there are in JuMP many ways of doing the same thing. I'm only going to focus on what I think is the simplest ones. But if you want to do something that is a bit trickier, I invite you to look at the documentation and look at other ways that you could possibly do things. But for the purpose of this talk, I will try to focus on what the simplest approach is. Okay, so now we have x and y. X and y's are not only variables in the model, they're variables that I can access directly from Julia. So remember, y, I can access variable y1 and y2, just like I can access x as if it were a matrix that I can index by I and j. And I will come back later to that to show you why it can be useful. Okay, so now we're going to set an objective. There is something that, so if you look at this formulation, you can see the objective as the following. The objective is linear, and the objective coefficient of xij is cij, and the objective coefficient of yj is fj. So my personal experience with existing solver APIs or modeling languages would be that for each variable, you declare its objective coefficient. This is not the way JuMP works. In JuMP, you specify this objective as an expression. So you're going to say my objective is to minimize the sum of the Cij times Xij plus the sum of Fj times Yj. And this is where a dynamic language like Julia allows you to do lots of things that can be fun and at the same time extremely weird. So I told you that I had X, and I can access X11. I can compute the sum of X11 and X12. This is something that I can do. I can do X11 plus 3 times X12. And I can add Y of 1. Okay? And you see that like this, I can build the objective function. So if I were to type it by hand, I would do f of 1 times y of 1 plus f of 2 times y of 2. And this gives me the fixed cost. Sorry. So the multiplication. And then I would have to add
all the objectives for the x variables. Now, of course, I'm not going to do this by hand. And imagine if n was like 1,000 and m was 10,000, this would be completely impossible to do. But x, in a way, is a vector, and y is a vector. So I can compute a dot product. If I have the right package, I can just do this. So here I'm going to compute the sum of fj times yj for j that goes from 1 to n. And this gives me the same thing as the expression that is here. And this is a very intuitive way of framing this sum here. It's exactly the sum of fj times yj. I could do it for only the first 3 values of j or something else, whatever you want. And I can do it also for the x variables. I can do the sum of cij times xij. Now this time I goes from 1 to m, and j goes from 1 to n. And if I do this, this is the objective terms for x. Now, exactly how this is represented by Julia, I can look at the type of this. And this is a generic affine expression. So it's an expression. I can sum expressions. So if you follow me, this is going to be one part of the objective. This is going to be the other part of the objective, and I'm just going to sum them to get the objective. So if I remove this, and I go back here, so the cost of the observing demand is the sum of xij times cij over this, and then I'm just going to copy paste this here. And now, how do I declare my objective? Well, just like we had the add variable macro, we have the add objective macro. So I declare that the objective of model, which I want to minimize, is equal to the cost of serving demand plus the fixed cost of building my facilities. And now if I look at my model, the objective is correctly written. So this might seem like a little bit unintuitive when you think of, but I just want to give the objective coefficient of x. But it can also be very useful if the objective coefficient for a given variable is given to you by a bunch of things that you need to add. Like imagine you had an extra cost for every time you're using a truck in a certain region of the town. And you have an extra cost for something else. And actually, if your facility has a number that is odd, then you have an extra cost, and so on and so forth. So then having the ability to build objectives like this as just naturally summing expressions allows you for a very flexible way of describing your objectives. And of course, nothing prevents you from doing this. Create the expression and pass it all at once. This is going to give you exactly the same result. So you can build stuff little by little, step by step, just like you would frame your optimization problem in real life, almost as if you were translating your word description of the problem. And this is it requires a bit of adaptation to get used to thinking in this way, but I think it's a very flexible and powerful way of modeling optimization problems. Questions so far? Everybody's dead. All right. So the only thing that is missing from our model are the constraints. Okay, we have all the variables. We've said that they're binaries. We have declared the objective. if I were to optimize that model right now, I would get some errors for a number of reasons, but this would just give me all variables equal to 0. If there's an objective, there's no constraint, every variable is binary, so the minimum cost is obviously put everything to 0. So before we can continue, we need to add the constraints. So remember, we have 2 types of constraints. They're here. First one is that every client must be served exactly once. So if I fix a client I, then the sum of xij over all the facilities should be equal to 1. So there's a very easy way of writing this. Let's just frame this this constraint. Okay, let's say I is equal to 1, and I want to say that the sum of xij for j goes from 1 to n should be equal to 1. So right now this is false, of course. So this is an expression x11 plus x12, and this is what I'm going to pass to JuMP. So JuMP is going to get this, and is going to parse it as the right expression. So I want to add a constraint to my model. Okay. And now things will get a little bit trickier. I want a constraint for every I in one M. Okay. So I'm going to comment on the right, and this is going to give you the signification of the every line. So this means that the constraints this to this model object. Okay. So everything that's created, I'm going to add it to model. There are M constraints, okay, and they're indexed by I. And I hope I will not get an error because I defined I here. So I'm just going to put K to be sure. So it's now xkj. And what is each constraint is the sum of xkj. The sum is over j. This should be exactly equal to 1. Now I'm going to print this model. All right, so I have all the binary variables. Now you see that for customer 1, x11 plus x12 is equal to 1, x21, x22 equal to 1, and so on and so forth. Okay, so coming back here, what I did with this thing was to say, I want to create constraints in this model. I want to have M constraints, and each constraint is going to be indexed by K. So I have constraints for K is equal to 1, K is equal to 2, until K is equal to M. And each constraint given K writes like this: the sum of xkj over j is equal to 1. Of course, this is not the only way of doing this, and I'm going to show you another way that is a bit more low level to do this for the second type of constraints. And I am not going to. So just so you know, if I were to run this again, it will add those constraints again. So I would have both duplicated. So be careful when you rerun cells in your notebook. Sometimes you may want to print your model just to make sure that you're not adding things too many times. Or you might get some errors, which is not the nicest thing, but okay, this should go here. All right. So now I am going to add constraints one by one for the second. You have a question?
Yes.
Go ahead.
Is it easy to edit a constraint? Like if I want one, say the second row, the right hand side to be 2, for example.
So in this syntax,
No, I have already added these constraints.
Yeah.
And then now I think I want to edit one of those constraints.
Yes.
How am I going to do it?
You will use something that is essentially telling you JuMP to change the constant term in this affine expression and changing to 2.
Okay.
But modifying problems will be done by Alexei afterwards. So far, I'm not doing anything that's too sophisticated. But yeah, there's a way to do it. It's not as straightforward as this, so I'm not diving into it right now. Okay, so now we want to edit the second batch of constraints. There are these ones. So for each j, I want that m times yj should be greater than the sum of all the clients that are being served by this facility. So I'm going to do this in a, I'm going to create those one by one. Okay, so now I'm iterating over j. And I want to add one constraint to the model. And hopefully this will work. I want the sum of xkj. I'm summing over k. So this is 1m and j goes from 1 to n. I want this to be less or equal than m times y of j. Okay, and this is not working because I forgot to write this. There we go. All right. Now, if we look at the model at the end, we have that all the clients that are being served by facility 1, the sum of these corresponding x's should be less than 5 times y1. And 5 is equal to m, so this is our model. Okay, so now we have a model. Our model is complete. We have all the variables, all the constraints. The objective is correctly defined. So what is missing? You can just read what's in the bottom to find the answer. So the one thing that we haven't defined yet is the solver. I have defined the model. I don't know how to solve it. And
just show the code, please.
Here. So this is adding the constraints one by one. Okay. Just like you could add them in a batch like this, you can have a slightly more low-level approach where you add them just one by one. So if you want to do weird things in J or have extra parameters that are not straightforward to define, you could do like some stuff that depends on J and then have something else here. All good? All right. So now just before we want to optimize, we need to tell JuMP which solver it should use. JuMP doesn't use the term solver. They use the term optimizer, which is essentially a solver. But for the purpose of this talk, we're always going to say optimizer. And I would like you to replace in your mind every occurrence of optimizer by solver, which will make things a little bit easier. Even you, Dominic. I know it's hard, but... So I set the optimizer of model, and I'm going to use a syntax that is I'm going to explain afterwards. Like this. And just like that, I said, remember the model that I just defined, this guy? I want you to solve it using GLPK. So GLPK is an open source mixed integer programming solver that I had you download and install and compile when you run this guy. So everything is loaded on your computer, and this should not be, so what follows should not be a problem. Okay. And now we can optimize. It's doing a few things in the background. Next time I would run this, this would be way faster, but that's it. And we get the optimal value. And now we would like maybe to know which of the facilities are opened. So remember we can access the variable wise. Sorry. So if y1, I can get its value by calling value of y1. So first facility is not open. And remember that the first facility had a cost that was super high. It was like 8,000. So we only opened the facility number 2 and we served everyone from there. And if we want to check that, say, no customer is being served by facility 1, we can look at the values of X. Now, there's a way to do that in a vectorized way in Julia that uses something that is called broadcast. So by adding this dot in front of the parenthesis here, I'm going to call value on all the coordinates of y. And this is going to return me a vector with the entries of y's in the optimal solution. So y1 was equal to 0 when 2 was equal to 1. I can do the same thing with x. And of course, it's going to be a matrix. And you see that all the customers are being served by the second facility. OK? Great.
What does that do with optimizers?
So remember, where is this? Here, when I was saying that there's something that's done in the cache, that's essentially what's happening. So with this command that is with optimizer thing, I'm telling it when you will instantiate the model, I want you to use a solver that you will instantiate from the glpk package using this function. So it will call, this is actually a function. It will instantiate a solver using this, and then load a glpk object through the glpk API using the model that I kept in the cache. That's very low level. If you have more questions, I see that Miles just arrived. So Miles, who's down there, is essentially the guy who coded JuMP. So if you have 2 hard questions for me, I will send them back to him. Yeah. So thanks a lot, by the way, for being here, Miles.
So you can't say, for example, set optimizer model glpk optimizer. That's not an optimizer? Or
no. Like so what you need to do, set optimizer, is a way to instantiate optimizers. Okay. And glpk.optimizer is a function, if I'm correct. You have other ways of doing this. You can declare glpk directly at the beginning, but it's like, I'm just giving you this. Believe me, it works, and proof it just worked. And I don't want to get more into the details. That's going to be for another workshop. OK, I think I'm going a bit too slow. Yeah, more questions?
I guess, what would be the difference between the optimize function and the solve function?
There is no solve function.
There is.
Oh, sorry, I forgot to tell you something. The version of JuMP that we're using is the development version, where essentially everything is changing. So whatever, if you ever used JuMP before in your life, forget everything you've ever learned and do whatever I say. And if you want to blame someone, blame the guy in the back. But there is no more. So if I'm correct, the solve function isn't in JuMP anymore. I guess it's to align with the syntax of the other APIs that would always use optimize. So if you were using Cplex and this was a Cplex object, you would call optimize. And if you were using MathOpt interface, you would call optimize. And then if you were using JuMP, you would say solve, which didn't really make much sense. So they changed it to optimize. Sorry about this detail. So the reason why we're using the development branch is because the older versions will probably be deprecated in a few months. So we wanted to give you something that is going to be, that should last for more than like 6 months until they do the next release. But this should be solid for at least 6 months, and then we can do another workshop. All right, another question? Okay. So we solved a model with integer variables, if you wanted to get the LP relaxation, you could essentially relax all variables to be integer and relax them to be continuous. So there's a function that does that, relaxes the integrality of variables. The only trick is that you also need to set bounds because it doesn't do that automatically. So if I wanted to do that, let me check at the solution. So I can only do it for one variable at a time. So here I'm going to iterate through all the variables that are in X, so all the xij's. If this variable is binary, and set it as a binary. So now it's a continuous. And I'm going to set a lower bound of 0, and I'm going to set an upper bound of 1.0. So essentially here I'm building the linear relaxation by relaxing the integrality constraints on X. And I can do the same for all the Y's. And do this. And I solve again, and I get the LP value. So set upper bound doesn't exist.
You have to specify var.
Oh yeah, thanks.
X as opposed to.
Thanks. Okay, and you see that the optimal value of the relaxed model is exactly the same one as before, because that example is too small. But if you were to increase the size of the problem, then you would see that the relaxed model would be slightly, well, consequently lower. There's a second part that I'm going to skip that works on not technically an extended formulation, but essentially an equivalent formulation that has more constraints. And the nice thing of this formulation is that it has a tighter LP relaxation. So if you want to solve facility location problems, you should never use this formulation. It's going to take you way too much time for large instances. So it's a much better approach to use this one, where essentially the constraint that was saying whenever I serve a client by a facility, I need to open that facility. This is described by these sets of constraints. There are many more of them, but this gives you a problem that is much tighter. So I'm going to skip through there. Essentially, you can do things just like I did before. Be careful, you need to specify the constraints correctly. And then you will see that the optimal LP relaxation is going to be much tighter compared to the compact one above. So if you want to experiment with that at home, just go back at the top of the notebook, change those values to like maybe 10 and 30, and this will give you nice instances to play with. Just don't forget to reinitialize the weights if you do that. All right. And I'm going to go to a second thing. There is a capacitated facility location. So now I'm saying each warehouse has a capacity. I cannot have infinitely many products in each facility. So I have a capacity Qj. And each of my customers has a demand AI. So now that capacity constraint is here, says that all the customers that you're serving from facility J, the sum of their demand should not exceed the capacity of the warehouse. And of course, you need to serve each customer only once. So you cannot send, if you have a very large customer, you cannot send one truck from one warehouse and another truck from another warehouse. You really can only use one truck, which may force you to open a new facility somewhere. Okay, so now I'm using a larger instance. So this model cap is going to be the model with capacity. And I'm going to go through this a bit faster because it's the same thing as before. So I'm creating variables. Creating Y variables, and they're all binaries. And then I'm going to copy paste. Okay. This.
So I add them now to model capacitated and not to the original model. So I'm going to rerun this because I made a mistake, and this is going to throw an error. Who can know what the error is going to be? So it's going to tell me that y is already defined in the model. I cannot define that variable twice. Actually, I can. And if you look at the model, so Miles, this is for you. If I print the model, you will see, no, model cap, sorry. You will see that I defined that y, I actually have it twice. So when I rerun that variable macro, it actually created those variables and then tried to bind the names to the Julia scope. And this is where it encountered an error. But the variables were still created in the model. So if you ever run into this and you run something and it tells you it's already defined, just recreate everything from scratch, unless it's taking you 2 hours. But this will allow you to go past this. And if you do this, of course, it's going to take forever. So do not print that model. It's going to take too much time and it's going to crash your browser. So the objective is going to be exactly the same thing as before. So I'm going to go back here, take the same expressions, now with the right dimensions. So just make sure that this is the right one. So I recreate constraints in the capacitated model. So these are for each customer. So this is y I in 1m. So now I'm using k. And I'm saying that the sum of x kj over j should be equal to 1. And we also have the capacity constraints. The capacity constraints are for the facilities, so we only have n of them. And now we need to say that, so it's okay here, the sum of a k, so the demand of customer k times whether that customer is served by facility j, this, put the sum here, so this is going to, that, in the comma. Okay. This should be less or equal than the capacity of the warehouse times whether that warehouse is open. Now, and just to tighten the LP relaxation, I'm also going to add those extra constraints that I was telling you before. So if I'm serving customer J from facility, customer K from facility J, then that facility should be open. Okay, and this will create that formulation plus extra constraints that will tighten the LP relaxation. Okay. So probably I made a mistake in my. So K. I was sending over this. Good. So this is a model, and it still has, well, whatever. I'm going to stop there because I want Alexis to take over. But essentially, you solve with those constraints, assuming everything is working. So I'm going to cheat, and I'm just going to solve the previous model from before. So here I'm setting an optimizer. I'm giving it a bit more parameters this time. I'm saying that I want to use an optimizer from GLPK. This time I want to print the output, and I'm going to give it a time limit of 10 seconds. Okay. Now, I'm going to solve that model. So this is solving with GLPK. So that log says that it starts with a simplex optimizer, solving the root relaxation, the LP relaxation, and then should start the integer, except remember I relaxed the integrality of all my variables here. So it's just solving the LP relaxation. So if you want to solve the integer, just don't relax integrality. You can get the, if you want to get the objective value of the optimal solution or the best solution that you found, you call the function objective value for the model. In the old one, it would have been something like either obj value or objval or get objval or something. And then you can change. So if say GLPK was not fast enough, it was supposed to happen with this model if I didn't get the error. So GLPK would have timed out. You can try something else. So you can try to use CBC. There's another solver. You can change the solver from the model by just using this call. So you don't have to change the API. You don't have to redo everything you did for formulating the model. You just say switch the solver. And this is where you're going to use this model that is cached. Instead of giving it to GLPK, you will give it to CBC. Something that now you can do directly from JuMP. And now this is being solved by CBC. So of course, it's only solving an LP, so it's probably calling CLP, trying all the things that it usually does, but it doesn't need any of them and proves optimalization. All right, that's pretty much all for me. So just to recap, I've given you an introduction onto how you can formulate models with JuMP. So first, you instantiate a model using the model function. Then you add variables, one by one, several by several, as much as you want. You can define an objective by essentially setting an expression that you can represent algebraically. And this is something that you can do because of Julia. This is not something you could do in pure Python, for instance, without significant overhead. This is definitely not something you could do in Fortran out of the box. You set the objective using the objective macro, and then you add constraints either in batch or one by one. Once you've done that, so now the model is ready, you give it a solver. Here I'm using GLPK, and you solve. And then you can get the objective value by calling objective value. Because you define those variables X and Y, you can access their values directly. And this is something we're going to use in a few minutes for solving with CSP. Any questions? Yes.
Quick one. When you unset a binary variable, does it become bounded between 0 and 1, or just completely free?
So the way JuMP will store that constraint that X is binary is to say that X should be either 0 or 1. But whereas Cplex would also implicitly add 0 and 1 lower and upper bounds, JuMP does not do that. So when you just unset the binaries, it will free the variable, and that's it. So you end up with the free variable. And I discovered that yesterday when I was coding this. So that's why I was adding lower and upper bounds every time. Okay, Alexis?
Yes.
So in the next part of the tutorial, we're going to do something slightly more involved. We're going to solve a TSP with 50 cities, not by hand, which is something that other people did 50 years ago by hand, but in a slightly longer amount of time. You want to go? Ouais. Il y a les... Bah ça c'est ton... Non, pardon. Il est là. T'as le notebook. Ouais. Ok. Je te mets en français. C'est bon? Ok.
Yeah, if you want to just raise a question.
So for this part of this tutorial, we talk about another problem, the asymmetric traveling salesman problem. Sorry, okay. For the idea of this project is to do a road trip with friends for this summer in Quebec. For the moment, we only have 9 cities. So for these 2 lines, we can load the distance between each cities, and the other one after the cities that we want to travel. And we want to modelize this problem. So we want to minimize the distance between each city. We only want to have only 1 cycle between these 9 cities. For each city, we only want to come in 1 time and left it also 1 time. We can teleport and loop over the same city, because if we did that, we will each variable will be equal to 0, because we can teleport between cities. So it's important to have this constraint. And this important and difficult constraint is to eliminate all subtools that we have in our model. Because if we don't do that, naturally the solver will find some subtools, and we only want 1 tool between all cities. For the modelization, we want to use a variable called xag, which is a binary variable. We set it to 1 if you travel from the city I to city G, and the omega subset is all the cities that we want to travel. So with this line, we allow the distance between each city. This line helps us to see what city we want to travel. This small function will compute all the subsets between for vector. So for example, if you want to compute the subset between 1 and 9 and 5, we'll do that thing. And we will use this function to eliminate all the subsets, all the subtools, sorry, of our model. So like before with Matthew, we saw how to modelize the problem. For this function, take a matrix distance D and an optimizer. For firstly, we read the number of cities. Matthew had some tests to verify that we don't give too high dimension problem. So first, we create the model, MIP. We create the different variables, which are all binary, and we set the object type. For that, sorry, for MIP. So what is our object type? Is to the distance, the dot between the distance and the variable xig. So we can do that thing. The sum between xig and the distance. B equal 1 to n. G equal 1 to n. So there will be our objective function. Yes.
It's capital N.
Yes, sorry.
We need to specify minimize.
So we want to minimize this function. And after, we need to add the other constraint. So the first one is that we only want to come 1 time in the city for each city. Sorry. Okay. The constraint. So for model, we want that the sum of each row, each column, or matrix X is 1. So we have the stochastic matrix. So the sum of xig. Is equal to 1. At the same time, that we want to come only one time in each city, and left on the city only one time also. Lip over x a 1, 2. So that will be the first two constraints. Yes.
Sorry, the name of X is capital S.
Yeah, thank you. It's fine. Then we don't want to loop over a city. Finish my loop. Then for each city, we force the variable to be equal to 0, sorry, for constraint. Permit. So that xkk is equal to 0. So this constraint goes there. And after, the most difficult constraint is to eliminate all the subtool. For that, we will compute the different subtool, the different possible subtools, like this. Will be like this, and we will loop over the different subtools. For subtool in T, we compute the length of the subtool. Like this. We compute the length of the subtool. Right. And after we add the constraint. So for each subtool, we want that subtool is the distance is less than the number of city, -1, less 1. So it will be like this. From it, the sum between x a 1 for k 1.
You mean all of those subsets? Like all of those subgroups?
Sorry?
The functions are also subsets.
Yeah, we compute. All the subsets were computed with the previous function.
Yeah, I changed the names. It's all subsets now, not also tools.
All subsets. Okay. Thank you, Mathieu.
Yes, go on.
For like this, and we need to add the last term so that x is t and st1 is less and -1 like this. Because our TSP is asymmetric, we need to do the same thing in the other side. Yes, thank you much.
Also on the first constraint.
First constraint, this one? Yeah.
Capitalize there.
Okay. Actually, change it.
So this is what happens when you change your naming conventions the day before the workshop.
For the moment, we have our model. We have the constraint of the subtools. Each city only have one predecessor and one successor. No city can be its own predecessor and successor. For once this thing is done, we can run the function. I will do this function. So it will create the model. In the same time, we will give it an optimizer. and at the end, it will return the matrix X with a connection between each city. We'll solve it with two solvers. If I write correctly the model, it will be 4. Hope so. No. So did I run everything before? X. So, G, it will be there, I think. Access to 0. Okay.
Une 41. Là, dans l'affichage des cellules, pour venir en ligne. Okay. This is fine.
Okay. Ah oui, yes, I remember. We want to verify that the subtour is between 2 and that's 1. It worked. So we have the solution. For CBC, we have a lot of outputs. So at the end, we have this matrix. We can solve also this problem with GLPK. And normally, we will have the same matrix. Okay, with the optimal tour length. And I code a small function that returns the trip between the cities. So it will analyze this solution and compute and return the list by order of the trip. So if you want to do the smallest distance trip between these 9 cities, we'll first begin to Montreal, then go to Yule and as well. For this is a small model. The problem with this model is that we are around 1,000 constraints. But if we want more city, like we will see in the other example, it's not possible to have these constraints. Those constraints. This constraint of subtour is there are too many constraints for a model. We'll need the following things. We will add the same model without this constraint, solve it, and relax it in the model after. So we will analyze the solution, see what subtour was activated, and add the constraint we will the constraint at each step to a model. For our model, what trip? So for something, I have distance for other cities in the United States. A function that finds the subtour that we will implement it together. And the Matthew had also some tests for verifying that the subtour are working well. This function is what we'll do dynamically between each step. So we'll add the subtour at each step. Thanks to relaxation. So basic formulation. So there we have our model without the subtour constraint. It will be essentially the 3 first constraint. This one. Oh, basic model. Okay. Okay, I will add the variable also. For the variable, for the objective function, we can formulate it in another differently. We can do that thing. The dot between each element of the two matrices. simpler implementation. So we have that, and now we will have to eliminate and analyze the subtool. For that, we need to implement this function and find the subtool.
Oh, I think you can let them try to find it.
Yeah.
Implement it.
Okay.
It took me some time, so I don't want to give them the answer too fast.
Okay.
Still have half an hour.
Yeah. We can give you 5 minutes to find
So
it.
the relaxation
At each
from
step.
the solution.
Oh yeah.
Yeah. So remember that the solution that you get is all binaries.
It's binaries.
Yeah. Yeah, which makes the analysis easier.
If we have some question for the implementation, you can ask Mathieu.
If you want to cheat, on the repository, we have a branch master that is the one that you all downloaded. There's a branch called solutions in which you actually have the solutions. So we still have half an hour before the end of the workshop, but if you want to spend less than 45 seconds, you can always just look at the solution. Or you can try it. It should be more of a Julia exercise than an optimization exercise.
For the function add subtool, it will be the same as before. So for subtool, we'll add simply the constraint, but only for one subtool. We need to find all the subtool during the relaxation in this function.
Just next to the first one.
Which line?
We're checking if next is equal to first.
Yeah. If you want, after there will be an error if there are some tests, and I want to delete this one.
Ah, yeah, that's right.
So this function will analyze our solution X and return each subtool that is found inside the matrix. So first it begins by the first component, and when it finishes subtool, it will analyze the first city which hasn't been visited before. And like this, it will be found the different subtool of matrix. And before we found the solution, we will have at least 2 subtools at each step. At the end, we return all the subtools. Yeah. So we have a function that will compute the different subtool. During this, when we solve the
run the tests.
Great idea. And it's not defined.
So
it will be in cap. It's in cap.
Go to line 8 and change capital N into small n. Yes, it should work.
Yeah, it's false. For when we have that, so we have a basic model. At each step, we optimize.
Sorry, maybe because I spent at least 25 minutes coding this yesterday, I want to spend at least 25 seconds explaining what this is doing. So here we're given something that we hope is a tour, but it's not a tour. So it's an integer solution to, can you go up to the foundation?
Yeah.
All the way up. Yeah, here. So it's a solution to that integer model with only a subset of those constraints. So we get a binary X that may have subtours. So when you have a subtour, it means instead of going through all the cities one by one, you go like from 1 to 2 to 3 and back to 1, and then you teleport, and then you do another 3 or 4 cities and so on. This is called a subtour. And to make sure that you have none of these, you need all those exponentially many constraints. And here we're adding them iteratively. So at each iteration, we get an X that may violate some of those constraints. And a way to find a constraint that is violated is just to find those subtours. So whenever you're teleporting in this TSP. And the function that Alexis just coded exploits the fact that X is integer, so you know which city is after which city. So you start from city number 1, and you keep going for the arcs that are given by X. And when you come back to city number 1, either you went through all the cities, in which case you had a valid tour, or you didn't go through all the cities, in which you have what is called a subtour. And that's the first one. Once you have the first one, you go, so you teleport to a city that you haven't visited, and you look, you cycle through the tour again, you get a new subtour, and so on and so forth.
for people who have a more combinatorics mind, this defines your permutation over the cities, and you're just trying to find the cycle decomposition of this permutation. So I tried yesterday to find a function that does that in Julia, but it doesn't seem to exist. So this is why we coded it by hand. And it's important to exploit the fact that it is integer. If the solution was fractional, it would be much less straightforward how to find those subtours, because you can't just like go through cities. You have a fractional arc, and it doesn't count as one. So that's it.
We can see, so for the first model, we have around 100 constraints, and for the second one, too much constraint. So it's impossible to add all of them to the model. It will take too much time, and I'm not sure that we can add all of them in the model before the computer crash. So we have the function to analyze the different subtours, and when we have that, we can run this second function that solves the TSP with relaxation. Yeah.
And yeah, the arguments.
Okay, thank you, Michael. And it should be. We try to solve it. But no, not fine. But it's still. This thing.
Oh, it's because you were using same line on the same two lines. It's x of s of s. At the end of line 9, line 10, you have a capital T.
Yeah, thank you, Michael. Okay, should be good. We'll compute the first function to be sure. Which was the solver? JPK. Okay. You change it now? I use
The CBC will output by default, so we end up having all the logs of CBC.
Okay. Today, I have a solution. Out of two, also a solution today.
Oh, you probably put the
You say 100?
what?
Yeah. And if I use CBC? What changed between yesterday? We have the same model. It worked. You can analyze our tool. Yeah, we have some tool. We see that 2 times we have the same. Yeah.
So if you go through the log of the sort TSP2, so here at each line you have the number of iteration. So we've done
Sorry.
Here, yeah. So at iteration 60, for instance, we had a tentative tour that is not a tour that had value 15,166. So this is a valid lower bound on the optimal value of the TSP problem. And we have added only about 480 subtours compared to the 2 to the 50 ones that we have in only 13.5 seconds.
I found the problem, I think. At the end, we forgot to compute the subtour. We need to find the subtour at each iteration. We didn't do that. So no? Where is the subtour?
Line 46.
Oh yeah, you're right.
Oh, it's just iterating.
Okay. one. But normally, if you have a good TSP, we'll find this solution between the different cities. And before we can verify with that we have the good solution, but I think there's some problem. Maybe we need to increase the iteration number.
Eventually to converge. So this is a very stupid way of implementing that, because in practice you do not want to solve the MIP at each iteration, you just want to solve an LP and then add those subtour eliminations whenever you want to, you think you have a good solution. And this you typically do using a callback.
Yes.
So if you're familiar with solvers, the callback is essentially whenever Cplex does something, it will call a function that is yours. And so it will give you, say, the current fractional solution. You find a tour and you add a cut. The thing is that right now, in the development version of JuMP, there is no way to define callbacks generically over all solvers. So you would have to go through the specific API of GLPK, and that's where things get a bit uglier. So from the JuMP model, you will have to go into the guts of the thing, extract the GLPK object, define a callback on that, and run your model like this. So as long as you do things that are simple, it's good. But right now, callbacks with JuMP not possible.
We hope so. I'm not sure that we will converge eventually.
Any questions? JuMP or something else? ABC is desperately waiting.
It worked yesterday. Maybe we did a mistake yesterday.
It's totally random.
Yeah. Do you have any question about TSP? It's basic modelization and formulation. And we can simplify also the expression because we solve symmetric TSP, and the first modelization and formulation is for asymmetric problems. But we want to use an interesting example is the word trait in the Quebec and United States. More applied problem.
So I do have a question. Who told you were going to have vacation in the summer?
No, don't cover.
Well, why is the separation problem especially difficult to implement? Combine the subtour, so the behavior relaxation, and then solve the separation problem.
So I don't know on the top of my head how to do it when you have a fractional solution.
You solve the separation problem, it gives you.
Yes, so the question then is, I give you a fractional solution to the TSP, how do you solve the separation problem? And
By solving another.
Yeah, another name, but it's not as straightforward as this case. So what changes is that because when you have integer variables, you can really take a city, look at the arc that is going out, and go to the next city, and so on. And then it's super easy to find the tours. You just like iterate until you come back to where you are. If I give you a fractional solution, maybe the outgoing arc is only 0.5, and the only one is 0.5. So it's not straightforward that you can. So even if you are finding a tour like this, with all the arcs having non-zero weights, it's not guaranteed that you would violate the subtour.
Oh, just by memory, I remember that if you take the fractional solution and you use these coefficients as put them in the object function of your separation problem, you can get what I remember they can model this as a maximum flow problem.
Yes.
Yeah. And then you can get your, I don't remember the actual model.
Okay, me neither.
Yeah.
So, and if you were implementing a callback, this is what you would do. You would get the fractional solution from the callback.
Yeah.
Compute the tool by solving your whatever separation problems in max flow. And then output the tool and give it to CPlex for the cuts. Or GRPK or CPC.
I don't think I will find the solution. Stopping it. We have subtools. Oh, sorry for everyone. I wanted that this example work. But no workshop for this summer. Maybe next year.
Yeah, so you can really see the subtools here. You're always doing the same. You're going through the right brothers with the center over and over and over again.
Maybe if we change some, no, I'm not sure. I come from the problem.
Maybe we made a mistake in the implementation.
Yeah, it's possible.
Okay. So all the notebooks that we presented today, you can find them on the repository, either with the gaps, like the one we gave you today on the master branch, or you can check out the solution branch that we need to update today to change a few things, but we're going to have a working version in those notebooks.
I found the problem, Mathieu. Forget to say the number variable. Find subtools. You have 2 parameters.
No, I changed to one.
Because we did on the correction.
Yeah, so that's why I said we need to update the solution branch.
Okay.
The log is fine. The objective function is increasing and it's cutting stuff.
I think so.
Try to run it with the first example. With 10 and D.
Oh.
And so now you need to remove the N46 of TSP2. Find subtours of just X.
46.
Remove the N.
Yeah. Yeah, that's it.
It's just the size of the problem.
This is the problem. I think we did a mistake and we saw it yesterday. Or maybe with a live on YouTube. The process less fast.
Earlier, I had like 1,000 subtool elimination
Yeah.
constraints. Now just 69. It's the number
Yeah.
of possible.
The number constraint become exponential.
Yeah.
But you can find the subtool of if the number of subtools is too important. During the resolution, you say?
What?
I don't understand what you want to say to me.
I just made a comment. I told you like there is a clear decrease between the number of constraints
Oh, okay.
in the beginning and now from 1,000 to the 69.
Okay, that's all for us.
Thank you, everyone.
So if you have further questions, like I said, Abel is going to be here for an extra 2 weeks. Dominique is going to be here for an extra longer period of time. So are Alex and I. So if you want to talk about Julia, about nonlinear optimization, about modeling, or if you have things that you would like workshops there to be about, don't hesitate to